Hello, everyone, and welcome to the seminar for categorytheory.zulipchat.com, organized by Jean-Baptiste Vianney and myself, Eric Downs. Today's speaker is Dr. Urs Schreiber, a research scientist at NYU Abu Dhabi who has done work in topological quantum mechanics, homology, and today's topic, higher topos theory in physics. A link for new members is in the chat. I'll put it in there now. And Urs, when you are ready, please let us know if you would prefer that people ask questions or hold them until the end.
Oh, yeah, absolutely. Please do ask questions. I think that's exactly the right kind of topic for asking questions during the talk.
Great. Okay, and then there will be a discussion in the topic. If you need help, I can direct you there. Just reach out to me. All right, go ahead, Urs. It's all you.
All right. Thank you very much indeed for the invitation. I'm glad to have the opportunity to speak. So I was invited, if I recall correctly, to present pretty much the content of this encyclopedia article that I recently wrote for the Encyclopedia of Mathematical Physics that is planned to be published later this year, which is written, and as will be my talk, mostly for an audience of people who are not well familiar with category theory, but are interested in physics and mathematical physics. And the point of the article, as well as of the talk today, is to explain in an elementary way how seemingly sophisticated topics of category and topos theory actually not only useful in physics, but are sort of secretly being used anyway by, informally by physicists, in the sense that they do something without formalizing it that is actually neatly captured by topos theory, and particularly by higher topos theory, so that this theory provides, theoretical underpinning for what is actually happening in physics, and thus provides, the opportunity to more sharply identify definitions, hence open problems, and maybe then to attack them and solve them. So I'm not planning to present any deep theorems in category theory. I'm just alluding to basic concepts of topos theory, actually, that I imagine, I don't know, most of you actually know. The point of the talk is to explain how this is actually used or to be used in physics, assuming that most of the audience is not actually maybe well familiar with fundamentals of modern physics. So it's meant to be basic, and yet I think there's a deep point here, which is worth highlighting. So with that out of the way, let me jump into the file. So as I already said pre-recording, I'm taking the liberty of essentially just walking you through this article. I don't have, the usual slides prepared, but don't worry, don't look at the text. We're going to just be looking at the diagrams, and they play the same role as slides. But of course, if anybody wants to see more details, there's this text around it. So there's a starting remark on what category theory is. I can jump over that, and I'll dive right into this main thesis of what this is all about. Let me just try to shrink this little window here. All right. So what we're going to discuss is toposes as a place. Well, that's the original meaning of topos in Greek, of course, for mathematical physics. And the reason why I'm giving, why there is something to be said here is that I claim the usual motivation for toposes that you will see in essentially all, if not actually all, introductions to topos theory is not the one that we're going to be concerned with. So the usual motivation of a topos is that, or the usual first example, the motivating example, is that you look on the category of sheaves on a fixed topological space. And sorry, is there a question? Okay. And the categories of sheaves on a fixed topological space, they're also known as the petit toposes. They are the most common examples that will always be given at the beginning, or some version of it. And that is crucially not the example we'll be concerned with. Of course, these toposes also, play a role somewhere in physics. They cannot not play a role given how, generally important they are. But the key point that all of my, discussion here hinges on is that what sort of actually more deeply fundamentally matters in physics are what's called gros toposes, those that are categories not to be thought of as sheaves on a fixed topological space, but rather understood as categories of all the spaces that we care about in a given context in physics. And they're still sheaves, of course, because we're going to be speaking about Grothendieck toposes. These Grot toposes are still sheaf toposes, but not on a fixed topological space or on a fixed scheme or any other given space, but they're sheaves on categories of probe spaces, on test spaces. And that's my first little diagram here, which I ask you to just focus on this box here, which I'm going to say a few words about now. So you may know or may not know, I don't know. If you've ever looked at the physics literature, you see that there's a strange looking mechanism going on where physicists will write down simple looking formulas in coordinates, always assuming a fixed coordinate chart, and then at some point jump away from that by some what looks like a leap of faith and speak about global spaces, which they still imagine to be described by these coordinate manipulations, which can sometimes be quite confusing because they do things with these coordinates that do not have an evident, unless you have the right theory, which is of course what I'm going to speak about, that do not have an immediate global meaning. For instance, to start in this little table here, the most basic example of a probe space that physicists will consider are just what are called Cartesian spaces. You may know these as Euclidean spaces, something, just the powers of R. These are, if you wish, the standard coordinate charts. And of course, since many centuries, people have been working on these. And, at the beginning of the last century, it was a big deal to understand that it's not, to abstract away from these charts, to understand that in physics, it's not the actual chart that matters, but that there's a global space which can somehow be probed by these charts, where you can lay out these coordinate charts in it, but the space is different from any of its charts. Nevertheless, working in coordinates led physicists to generalizations of spaces that are actually quite sophisticated. They took mathematicians a long time, actually a long, long time, to come to grips with. Namely, one thing that you see physicists do all of the time, for instance, at the beginning of Feynman's thesis, to just name one example, is they will say, okay, let's suppose we have a coordinate which, however, its values are so small that if you square it, taking a number smaller than 1 and squaring it makes it even smaller. So you say, okay, let's suppose we have a coordinate number of sorts that is so small that if you square it, it actually vanishes identically. This is something one can easily write down in coordinates. It essentially means you work with some quotient ring of some polynomial ring, the ring of dual numbers, if you've seen these things. But then, as I said before, you kind of imagine in physics that, well, you can just run with this and apply this trick to globally non-trivial situations where it's not so clear, that you have a coordinate chart, or if you have one, how it's equivalent to other ones. So that's what I'm denoting here. I'll come to this later in the talk. That's what I'm denoting by this D here, which is meant to be short for disk, an infinitesimal disk. So what this means is that in physics literature, people easily imagine, they've done this for now a century, essentially, that in addition to ordinary coordinates modeled on Cartesian space, there can be these infinitesimals. But once you do this, it's actually easy, once you have the liberty to induce nilpotent elements in your coordinate ring, well, why not make them, why not change their commutativity properties? And as you know, this is actually, this is not just a whimsical theoretical idea, but of deep, profound relevance for reality, actually, in that looking at infinitesimal coordinates of sorts that are also anti-commuting, if the ring they form is actually an anti-commuting ring, that is, well, mathematically, that's the foundations of supergeometry, but physically, that actually encodes the existence of fermionic particles. And that means it's pretty much everything that you see and touch around yourself all consists of fermions. So, it's somehow remarkable how an aspect of reality that is so fundamental, essentially everything, except of light and gravitational force that you feel, everything you are and touch and feel consists of fermions, which mathematically means that somehow you're dealing with spaces whose coordinate functions are anti-commuting. And it's it used to be an open question. Physicists just went ahead and just said, okay, but I can switch my coordinates on paper and introduce a sign. You can just do it algebraically, but what does it actually mean globally? So we'll come to that and show how Topos theory actually has something to say about this. And from there it continues. Next, you want to speak about what's called gauge theories. That's the rest, if you wish. Reality consists of fermions. That's the stuff that things consist of, and then there's force fields between them, which are described by what in physics is known as gauge theory. I'm going a bit quick now, but it's kind of interesting to notice that the next aspect in this way of adding more structure to your coordinate charts has another very profound meaning physically. It's called bosons or gauge symmetries. And we'll see that this is delta. This is meant to indicate a simplex, modeling a higher morphism in a higher groupoid. Adding that kind of to your coordinate rings, in a sense, allows people, and they do this implicitly, to speak about gauge transformations and eventually higher gauge transformations. And one can keep going. I'll maybe not say anything right now about the further aspects here, even though they're quite important. Let's see how much time there is in the end to speak about this. The point here, and now I'm coming to the actual content of the Topos theory. The point is just to bear in mind, or to highlight, that ever more sophisticated notions of coordinate charts of sorts drive modern physics, very much so. And the question is, well, okay, you can algebraically handle these things, but what does it actually mean? What are spaces of fields, say, that are described as such coordinate charts? And so we'll be very simple-minded now, but kind of rederive the notion of a sheaf now from just asking what it would actually mean now to have a space. Think of a space-time, or more generally, and more importantly, maybe, what's called a moduli space of fields. So suppose you have some physical system and you want to look at not just the space it's defined on, say ordinary space-time, or some crystal in the laboratory, but think about the space of all its configurations, like all the possible positions of particles, or more generally, and we'll come to this, of course, all the fields that make up this system. Well, okay, and then you have one of these coordinate charts, and we'll focus to start with on just the simple Rn. So we'll do something, we really go back to the basics here and just ask the most basic questions. What if we don't presuppose that these spaces in physics, and they're not, what if we don't presuppose that there are smooth manifolds, or manifolds at all, which are locally isomorphic, locally diffeomorphic to Rn? What if there are more general things, spaces, that of which we only know that they can be probed by Rn? So we want to say the only thing we can really do is we have this imaginary or not yet defined space there, and the only way to get access to it is that we map out these coordinate charts into it. We map it into it, not even diffeomorphically in any way, just mapping it into it. And this is actually a very, if you think about it, just as a side remark, this is a very kind of fundamental way of thinking about actual spaces in our actual physical experience. The space we perceive, we don't perceive it as a set of points, all pre-specified with extra structure in it, but we probe it by, for instance, bouncing photons off it and receiving the image with our eyes, or touching something with our hands. And you get an image of what the space around you is by making little local probes and eventually getting a picture. And it's that intuitive, I think, very nice idea that we can nicely formalize now by some category theory. Let me just walk through this. This is just a whimsical, if you will, way of rederiving the sheaf notion, but it carries in it the seed of all the generalizations that are to come. So I want to spend some time on this, even though it's almost all tautological. It may seem, it's one of these Yoneda-like tautologies that are deep and worthwhile of our attention. Anyway, so we want to bootstrap a kind of space into existence. Suppose I imagine a space, and you have to understand what space it is. And what you can do is you can take these probes, which in this case are Rn's, and ask, what is the set of ways of mapping in whatever geometric way is the appropriate one? In this case, we should be thinking of smooth maps, mapping these Rn's into X. So, right, this is just a set of ways of mapping Rn smoothly into X. And so if you want to have any chance to actually understand which space I'm thinking of, I need to give you a little bit, I need to, in giving you this law, which plots, I'm going to call them, which plots the space has for any probe, it needs to satisfy some basic consistency conditions for you to be able to say, well, there's actually such a space. You're not just making stuff up. And let's just look at what these consistency conditions are. So I have some text here, but we can just look at it in the diagrams. But I'll leave the text there for anyone who wants to look at it. Maybe it just says the obvious one. So here's our imaginary space X, and we have our probe Rn, and we want to think of this plot, which a priori is just an abstract thing. We're just speaking of a set of plots here, but of course we do want to eventually think of it as being an actual map. Just keeping in mind that at this stage of bootstrapping our would-be space into existence. There's no notion yet. It's not there yet. We haven't even defined the category of these things yet. So there's no actual map yet, which would be that plot. But since we want to think of it this way, I'm drawing it already as an arrow. So this is an abstract arrow, if you wish, not a morphism yet, even though, of course, the whole point of the exercise is that in just a moment, it will actually become a morphism. But for the moment, we would just say, let there be a plot phi of x, a way of would be mapping Rn into x. Well, then basic consistency conditions should involve the following. If you have a smooth map between plots, say from an Rn prime to Rn, then since we do want to think of this as a smooth map to this would-be space X, well, then precomposing it should give us another plot, which we do want to denote in the usual way as being phi after F. So the first consistency condition is that if I hand you these sets of plots for all probes, then I need to be able to tell you for each smooth map between probes how that map kind of pulls back plots from one probe space to another probe space. But in order for that in turn to be consistent, it should be the case that if I do this twice, if I next pull back this probe along another smooth map of probes F prime, right? The point is, let me just highlight, it's these smooth maps of probes are the things we're meant to understand, right? We know since these are our test spaces, these are just maps between coordinate charts. So these are things we understand, whereas X is something we do not understand yet, possibly. And so the obvious condition is that, of course, if you pull back twice, that should be the same thing, since we do understand what maps of smooth probes are. That should be the same thing as having pulled back our original probe along the composite here, which says that this diagram commutes. And of course, all I'm saying here is actually that the set of plots, the assignment of plots from the previous slides here, this assignment that to each probe space assigns the way of probing my space by the given, or plotting out into my space a given probe, they should form a pre-sheaf of sets. That's really what this says. It just says that probing should be compatible under the smooth maps that are already defined on my probes. Then the second important condition is, of course, that there's some notion of locality here. These probes may be large, like this Rn, if X is, say, some space-time, there's nothing that prevents Rn from mapping through the whole universe. But in order to just understand space-time, of course, you don't imagine that you need to lay out coordinate charts through the entire universe or even beyond your laboratory. You should be able to understand what the space is like by probing it locally and patching the little probes together where they match. Well, that's just our next condition. We say, suppose you have two probes. Remember, these are our would-be arrows that are at the moment just arrows, not morphisms yet, but drawn as arrows. So suppose this is an Rn, but I'm writing it as a U1 now to put you in the mindset of thinking of it as being part of a cover of a given Rn. So suppose here's an Rn, you have a probe by that, you have another probe, and they happen to cover, or at least to overlap, as subsets of a given Rn. And then we want to say, well, if that is the case, if you have such a situation, right, where two probes actually overlap and coincide, on an ambient probe space, well then they should actually, and that's the outer commutativity of this diagram, they should actually, well, sorry, maybe I mixed that up here. I should say, if you have this outer diagram, right, you have this plot, and they coincide in the outer diagram commute on the intersection of these plots, well, then you should be able to glue them together into a plot of this Rn, which is covered by these two patches. So I'm drawing it here just for two patches, but of course, you can do this for any number of patches. And the condition that I'm phrasing here, just by appealing to the physical intuition of probing a space locally and building a picture of the full space by gluing these probes where they agree, that is just the condition that the pre-sheaf of plots, which we had motivated previously, is a sheaf with respect to the obvious Rote-Dick pre-topology, as it were, of good open covers, say, on Rns. Right. So remember, we're our site, as it were, right? The category of all probe spaces. It's not a topological space. It's not a fixed manifold. It's not a fixed Rn. It's the category of all the Rns for any n. But nevertheless, I can speak about what it means to cover a given one. And this gluing condition says that my space is locally probable. Right, so these two definitions just tell me that these would be generalized spaces that we can probe with smooth Rns. They're just sheaves on the category of Cartesian spaces with smooth maps between them and equipped with the Grothendieck pre-topology of good open covers, say, open covers. Well, but then let's think about if we really get the corresponding category. So we need to ask, well, what are the morphisms of these would-be spaces now? And in the same spirit of saying that everything is kind of probed by our test spaces, we should ask, well, there's a smooth map between two such smooth sets, as I'm going to call them, two such sheaves on Cartesian spaces. It should just be any assignment, well, that takes a plot of say a plot phi here of x, and if I have a smooth, if I had an actual smooth map, and these were an actual smooth map to x, well, then I should be able to push it forward to compose these two things. And since the result is meant to be a smooth map of y, the result must be a plot of y. So my morphism of these smooth sets, these generalized smooth spaces, should be an assignment that takes plots of x to plots of y, thought of as being the composition operation simply, such that, again, this is compatible with precomposition of the actual smooth maps between these RNs. And if you just stare at this diagram a bit, you see that this is exactly just the definition of a morphism of pre-sheaves on card space. It's just, object-wise, you map these plots to each other such that this assignment is compatible under composition. And so this way, we arrive at the maybe not surprising, but actually useful statement that we want to be speaking of the category of smooth sets, say, that's how I called it, or maybe smooth spaces or smooth zero types or something, if we think ahead of the higher categorical generalization. It's just being the category of sheaves on the side of Cartesian spaces, the way I just described. And, just for fun, maybe, even though, as I said, all of this is in a way tautology, but it's maybe still good to amplify this given the physics picture we have here, because it helps us with the generalizations that we'll come to. Of course, now, given that we've bootstrapped now this notion of generalized physical spaces, smooth spaces, out of existence by just saying what it is like to probe them, we observe that, of course, as the first examples of such generalized spaces are our ordinary spaces. So if you take an ordinary Cartesian space, or in fact any ordinary smooth manifold with ordinary point set definition of smooth manifolds, you can easily produce or regard them as a smooth set by just saying, well, their plots, the plots of a smooth manifold N in the above sense, should just be the ordinary smooth maps. Plots into M should just be the standard smooth functions. So assuming now we already have, as we do, right, the standard theory of smooth manifolds, that standard theory embeds into our generalized context of smooth sets by just taking the plots to be the evident ones. And then, of course, there's nothing but, here's the Yoneda lemma, and here's what could be called the external Yoneda lemma or something. It's just a canonical embedding of the test spaces into the generalized spaces. And I want to just highlight a fun thing here. The role of the Yoneda lemma in this business is because if you just, if you haven't heard of Sheaf and Topos theory and the Yoneda lemma before, at this point, you should say, wait a second, there is a potential inconsistency here, which we need to deal with or rule out. Namely, now that we have this embedding, there is potentially now two different meanings of what it means to map between to probe a smooth set. Because once we have this embedding, our Cartesian spaces are now among the category of smooth sets. And with that in hand, we can now, given that we've just defined morphisms of these smooth sets, we can now speak of the sort of actual maps from a Cartesian space into a given smooth set X. Remember that before, all these arrows were hypothetical in the sense of, that's why I call it the bootstrap process. We did not actually have morphisms yet. We just declared there to be a set of things that we want to think of as these plots. But under this embedding now, these morphisms actually exist, namely, under Yoneda in the category of smooth sets. So a priori, there's an inconsistency now. It could happen. You could ask, right, whether the prescribed set of plots by a given Rn actually coincides with the actual maps from Rn into the given X. And of course, the Yoneda lemma, interestingly, I find this kind of entertaining, is exactly the statement that these two notions now coincide, that the prescribed plots, which are kind of, the values of our sheaf on a given Rn, are really just the homes from this representable, as it were, into X. So it says that this bootstrap process is actually consistent. It's a very important fundamental process, statement about this functorial geometry. Right, I should maybe amplify, even though I'm presenting it in this differential geometric example, this is really what I'm saying here, is really what Grothendieck, I think, actually amplified at the very end of the 50s or beginning of the 60s. We started talking about functorial geometry in the context of algebraic geometry and highlighted that at that point, you try to convince people to actually abandon the definition of schemes as local ring spaces and instead adopt what came to be called as the perspective of the functor of points. That's exactly what I'm describing here, just for smooth sets, right? Okay, so with that given, let's for maybe maybe for the sake of time, let me jump over this germ discussion. We can come to this. This is needed for suitably generalizing to the infinity toposes. But let's maybe come to some actual application in physics. So here's a paragraph on the general meaning of toposes, of course, which I don't have to repeat here. So here's the first fun actual application of this very simple setup that actually already solves actual problems that people are still, mathematical physicists, if you look at the literature, are still struggling with as we speak. So this is not an old hat, actually. This is still something that hasn't penetrated the community yet, what I'm describing now, even though it's the most simple consequence of this perspective of thinking of these smooth sets as being the right context for physical spaces. Namely, let's think about physical fields, right? So the key reason, one could say, why field theory in the sense of physics, the theory of physical fields, like the field of the electric field, the field of gravity, why field theory is notoriously hard, as you may have heard, much harder than the old, say, Newton time point mechanics, which is very well understood. The key reason is that the objects of interest in field theory, the degrees of freedom, as the physicists say, are fields, as the name suggests, namely maps from a given domain space, usually space-time, or maybe some space like the crystal. We analyze a crystalline material, or whatever your domain space is. But think of space-time, and then a field in the simplest picture, if there's no twists and gauge symmetries around, is a map that takes every point of space-time to a certain coefficient space of field values. For instance, if you're in a simple case of the Higgs field, this would be the complex number CF, and well, even that is oversimplified anyway. So for every point, there's some value of that field, and any such map is only one configuration of our physical system in field theory. And now we want to be speaking about the dynamics of a system. So we want to be speaking about the space of all these fields, which is a mapping space now. And what's the issue with that? Well, mapping spaces between, let's call it fields here. The space of all fields, in this simple example, is the space, whatever that means, of all maps, smooth maps in this case, from X to F. And the reason why this is actually, even though it's easily written down on paper here, why this is a subtle space for traditional differential geometry is that under very strict and unrealistic conditions only on X, can one give this space, which is not a finite dimensional manifold, can one give it the structure of an infinite dimensional, what's called a Fréchet manifold, where one tries to import the structure of ordinary finite dimensional smooth manifolds to the infinite dimensional setup. So only if X is compact can one give this space here, this mapping space in general, the structure of what's called an infinite dimensional smooth manifolds. But X being compact is usually an absurd assumption, which is contrary really to the intended applications. Remember, X is meant to be space-time. So certainly in the time direction, this is not compact. And whether it's compact in the space direction, it's a subject on cosmological discussion. It's not something we want to presuppose in our mathematical formalism. And in general, if X is not compact, then this space is just outside the realm of applicability of standard differential geometry. You cannot go and open a textbook on differential geometry, even in 2024, standard differential geometry, and find a discussion of these spaces. They just don't exist in the traditional context. And of course, now and this is one of the main motivations, of course, in our slightly enlarged perspective now of these generalized smooth sets, they easily exist, right? So first of all, just to mention this triviality here, first of all, we can easily speak, of course, of Cartesian products of our smooth sets just by saying that the plots of a Cartesian product of smooth sets is just the product, the pairs of their plots. And using that, we want to say that the defining property of such a mapping space should just be that the probes, say, the plots into the mapping space, well, what should they be? A point in here is meant to be a smooth map from X to F. So a U-parametrized smooth family of such points should be a U-parametrized families of maps from X to F. But such a map itself is just kind of an X-parametrized family of points in F smoothly. So together, this is clearly just the same thing as a U times X parametrized family of points in F, so to speak, even though we don't want to be speaking of points, of course, but maybe that helps with the intuition. So there's just the usual, of course, the usual internal Helm adjunction here that I'm writing down, which says that our mapping space, our internal Helm space, as it were, should be characterized by the fact that its U plots should just be the maps on this product space, U times X, which I can form since both U and X are smooth spaces and they have an obvious Cartesian product. So we can take this, again, as a bit of a bootstrap process, if you wish, depending on how you look at it. We can take this demand, this desire of what the smooth mapping space should be or should behave like as being its actual definition. We just say, well, we define it as a smooth set. Well, what do we have to do? We have to define its sets of plots. So take U to be some Rn. And we take its plots to be its U plots to just be the homomorphism of smooth sets from U times X. And of course, if you've ever seen basics of Topos theory, you know that you can prove this. This is the characterization of the internal Helm in sheaf toposes. This assignment is easily seen to be, first of all, pre-sheaf. It's also a sheaf on our side, and it satisfies kind of by construction our intended internal Helm adjunction. It does behave. It quacks like it looks like a mapping space. It is a mapping space. Certainly, as you can easily see, its underlying points are all the maps, and the smooth structure on it is just the evident one where you say a smooth family of maps should just be, just to repeat, should just be a single smooth map on this product. Now, the interesting thing is, which I'm just saying in text here, is that this simple definition, you might say, well, okay, I mean, this is obvious. Well, nothing can possibly be learned from this here, but quite the contrary is the case. So one can prove now that, that you go through literature and people have written out, of course, Fréchet, so suppose X is actually compact. People have, worked out the Fréchet manifold structure of these mapping spaces. But also Fréchet manifolds, of course, I haven't introduced them, but since they are infinite dimensional and smooth manifolds of sorts, they again have an obvious notion of plots, sort of again by an external Unetta embedding, also into a Fréchet smooth manifold. You can speak about the ordinary smooth maps from an Rn, because Rn's in particular are also Fréchet smooth manifolds. So we can look at the ordinary plots of a Fréchet smooth manifold, and as such, we can regard our Fréchet smooth manifold as a smooth set in our sheaf sense. And then it turns out, this quite remarkably, that under this embedding, the Unetta embedding of Fréchet manifolds into smooth sets, the complicated in the sense that it takes a lot of work, Fréchet mapping space for X compact actually coincides with this. It's just the internal Helm after embedding. And so one finds quite a powerful new context for dealing with field spaces here. And I should maybe advertise that if I can jump here, this is the context of, I've talked about this before in lecture notes on quantum field theory, but recently two members of our group have written this article, Field Theory by Higher Geometry 1, Smooth Sets of Fields, where they walk through all the standard constructions in classical field theory, Euler-Lagrange equations, equations of motion, variational calculus, in this language of smooth sets, using just these technologies. Maybe I should ask at this point if there's any questions so far. No? Does anybody hear me? Did I lose the audience?
Yes, we can hear you. No, you haven't lost us.
Okay.
If anyone has questions, just throw them in the chat, and that way Urs will know, or I can let him know.
Yeah, please read them out of there. I'm not checking the chat right now. I can't do that. I think.
Yeah, that's fine. I can do that. Yeah.
Okay. Right. So okay. So this was meant to so this shows like how the simple idea of looking at these sheaves of sheaf categories of generalized smooth spaces has some obvious application, and I'm going to slowly walk through slightly ever more richer, sophisticated examples of this. So I saw that the previous talk in this Zulip category theory talk series was on diffeological spaces, if I saw this correctly. And you should amplify at this point, of course, that diffeological spaces are a special case of smooth sets. Don't exhaust. There's more smooth sets than there are diffeological spaces. But diffeological spaces are exactly what in all traditional category theory or Topos theory literature are called the concrete objects, the concrete sheaves, namely a smooth, in general, since we did not define a smooth set as being, we didn't define it as a set of points with extra structure a priori. But we can still ask, a diffeological space, on the other hand, is defined to be, that's the way it's usually defined. It's a set also equipped with the number of plots. That's where I'm taking that name from, of course. I guess it's Patrick Iglesias-Semur's terminology, plots, which I'm adopting here. So anyway, so a diffeological space is defined by an underlying set, and we can ask, we can characterize this. We can say a smooth set X, can call it concrete if all its sets of plots from a given Rn are naturally embedded into the set of all, point set maps, just maps of sets of underlying points of Rn to the underlying points of X. So that means X. Suppose there is a set XS, the underlying. Suppose there is an underlying set of X, such that all the plots or the would-be smooth maps into X are actually a subset of the point set maps from Rn to this set. If that is the case, if such a set exists, then we abstractly we would say we are dealing with a concrete sheaf, and in this case, the concrete objects among smooth sets are exactly the diffeological spaces. And so everything you've heard about diffeological spaces, and maybe mapping spaces were advertised to you before in this context, is directly imported here faithfully again. But an interesting observation is that there's actually more smooth sets than the diffeological ones. Not every smooth set is a diffeological space. There are non-concrete ones, and they're actually extremely useful for certain applications in physics. So let me just highlight one example. Maybe switching is skipping over this. Namely, and this gets us to the point that will be important later on. Maybe I'm getting to this. We'll not be able to get to this due to the time we have. But later on, when we want to be speaking about modular spaces of higher gauge fields and higher gauge theories, we're building smooth sets or higher smooth spaces actually that are such that mapping into them, that they classify, that they modulate all our fields, so that a smooth map into them is the same thing as a possibly complicated field configuration on spacetime. And a simple archetype of that, simple but important archetype of the general situation is encountered with just thinking about differential forms, right? So suppose we want to build a classifying space of differential forms. So there's no way that such a thing can exist in traditional differential geometry, not even in diffeology. But if we just go with this general idea of plots, we can easily write it down. We want a space to be denoted omega de Rham here for the usual notation for differential forms of degree p, whatever that is. Well, if you don't know what this is, I don't know. It's just kind of defined hereby. So we want to say, well, it's meant to classify differential p forms, but that means since on any smooth manifold, say, but since Rn is a smooth manifold, well, it should be that the plots, which are meant to be maps into this, should just be the corresponding differential forms, right? Because if this is a classifying space, any such map should classify a differential form. That's kind of the definition. So I want to say the plots into it are actually the differential forms. It's easy to see because differential forms, they pull back and they glue. There's a sheaf of differential forms. So this thing, if you wish, the abstract sheaf of differential p forms on any Cartesian space, that is a smooth set. It's a sheaf on the category of Cartesian spaces. But it's highly non-concrete. If p is greater than 1 or greater than 0, then, for instance, it has this space here is a single point, right? Because the maps from R0 into this are the differential p forms, p greater than 0 on the point, but there's only a single one because the point is 0 dimensional. It cannot carry a positive dimensional differential form that is not 0. So there's a single point, the 0 form. You might think, well, if this were a diffeological space, it would have to be the trivial one, the point. But nevertheless, by its defining property, if p is greater than, if p equals 1, for instance, there's an infinite number of curves in this space corresponding to all the differential forms on R1. And in general, if P, for any P, there's an infinite set of p-dimensional curves in this smooth set. So it's a highly exotic space from traditional perspectives. For given P, it may have a single point, a single curve, a single surface you can find in there. But then suddenly when you reach P, there's this infinite number of p-dimensional maps into it. Well, nevertheless, from just basic yoga, you find now, even though we just define it by its plots on Rn, this is now a classifying space for differential forms on X. Essentially, if X is a smooth manifold. If X is a smooth manifold, it's by definition covered by Rn's, and then a simple yoga of sheaf theory tells you that the homomorphisms from X into this classifying space of differential forms is actually the set of differential forms on X. So this really classifies differential forms. And again, this is an example which in itself, if you do understand Topos theory already, it's a tautological trivial thing which might leave you wonder how anything can be gained thereby. But I have a simple example which maybe I just mentioned. This was geared towards an audience who may previously have heard about anomaly polynomials, which I cannot assume here. There is an important topic in quantum gauge field theory where people compute what's called anomaly polynomials, and all the literature does so on a given space-time manifold of some dimension. What do I have it here? Dimension n. And without much ado, they will start to be talking at some point about differential forms of degree n+2. And the reader in all these traditional discussions is left wondering how on earth we can be talking non-trivially about differential n+2 forms on a differential manifold n, given that in standard differential geometry, these just necessarily vanish just by degree reasons. And if you analyze what's actually happening in this physics literature, in the discussion of these anomaly polynomials, you can see that what they're actually describing is differential forms not on spacetime itself, but actually on the mapping space, the field space. And working through it, one finds that what these differential forms are actually defined by are not on the spacetime Xn itself, but on families where we probe the whole situation by some plot, by some probe space U. And so that everything gets parameterized not just by the actual spacetime points Xn, but also by these extra parameter points, which has the effect that it does actually make sense to speak about higher dimensional forms, which, just as in the previous case that we discussed, only appear once your extra parameters of probe directions exceeds a certain dimension. So this too, even though I've not really explained it here due to maybe time reasons, we can talk about this later. This too actually solves a conceptual issue in physics, which I bet most of the authors who actually work on this topic would not be able to give you a decent definition of if you ask them what they actually mean. Of course, this is known to some people. This is not entirely a novel observation that this kind, but some glimpse of this is available in the literature. But anyway, these smooth sets give very neat home to these things. Here's another point that I want to make regarding maybe constructivism. So let's look at this diagram here. If you open many of the standard introductions to Topos theory, instead of telling you anything of the kind that I did here relating to kind of hands-on geometry, they like to enter logical issues of foundations of mathematical logic. And at some point or other, of course, people will speak about the internal logic of a Topos and how it's an intuitionistic and not classical logic, which violates the axiom of choice. And to a novice reader who comes maybe from more of a physics background, as I used to many years back, it can seem quite mystifying how all of this actually plays a role in a topic that you might have thought is about describing space and geometry. And I want to highlight that it's just a bit of a, how should one say, it's not a very technically complicated point, but again, I think it's an important issue to understand. The role of the axiom of choice here, right? So if we're in the Topos, in the base Topos of sets, we're just talking about plane sets, not smooth sets or something. Then of course, one way to speak about the axiom of choice is to say that for every surjection of sets, plane set E surjecting onto plane set B, there is a section, right? That section just means there is a choice you can make for every point B. You can make a choice in this fiber space, the fiber of this projection, this fibration, this surjection over B. And if you're presented with this in sets, it may be a matter as it is. People debate whether or not You want this in your category of sets. There's pro and contra. You may be undecided whether this is an axiom you want to have in your set theory. But the point I want to amplify is that the whole point of this Topos theory is, of course, that all these situations make sense just as well in other sheaf toposes. And we might be thinking of the same situation in our context of smooth sets as we do in physics. Now, if these are not just plain sets, but smooth sets, then we certainly do not want any such surjection to have a section. Why not? Well, because this is really important for many deep phenomena in physics. Very deep phenomena, even at, in the standard model of particle physics related to instantons and QCD and anomaly freedom, is the fact that such a surjection, now in the smooth context, is in general, is a smooth fiber bundle. It may underlying it may be a non-trivial topological fiber bundle. Like, for instance, the simplest examples of these things, the famous Möbius band, or some non-trivial principal line bundle, as appears, for instance, in the discussion of Dirac monopoles in electromagnetism, or Abrikosov vortices and superconductors. So there's many situations in physics where you have a map of smooth sets here, such that in particular field configurations are maybe locally sections of such a bundle. But crucially, you do not want there to be a global section, because such a global section would actually mean that the bundle is, in a sense, trivial. So you will, if you are underlying set theory as an axiom of choice, you will be able to find by assumption, find such a section as a map of underlying sets of points, but it will not, in general, be smooth or even just continuous. So this just to highlight that, the sometimes mysterious or remote from physics seeming logical aspect of Topos theory has a very concrete meaning even here, where, for instance, the absence of the axiom of choice in our Topos is crucially related to all kinds of non-trivial topological effects that control many aspects of physics. Yeah, and so proceeding in this way, we'll see, and this is what I would say next, but I should check my time actually. Proceeding this way, we've been talking about smooth sets at the top of smooth sets, and proceeding in this way now, we can form kind of a bestiary of ever richer toposes of generalized spaces relevant for physics. We're just taking the previous philosophy, say, or heuristics of taking a fixed notion of coordinate chart. We were just talking about Rn so far, boosting it, say, maybe to infinite coordinates with infinitesimals, or with super functions, or with higher functions, and forming the corresponding generalized spaces by means of Topos theory. So that will be what I have to say next. But let me ask at this point if there's any questions so far, and maybe check how much time we have to say more. Yeah, I guess.
We have 10 minutes to the hour. Yeah, and then you're welcome to continue as long as you wish. We'll just let people ask questions.
Right. Yeah. So I mean, this would be a little point for a good point for a break if anybody wants to leave at this point. But maybe if there's interest, I could sketch the next example where we're bringing the infinitesimals, and then of course I should maybe say something about the actual higher aspect. Some gauge theory, maybe another 15 minutes or so, if there's interest. Okay, I'll just go ahead. You interrupt me.
Yes.
So let's so far, even though I did amplify some applications, but of course so far we're pretty much in a standard realm. We've just been talking about smooth functions in a sophisticated way, but now let's do something more sophisticated. Oh, just slightly, but still of interest. So, in the spirit of enlarging our coordinate charts, observe that there's the following general way of enlarging the standard coordinate functions on Rn's by using the following fact of differential geometry, which is kind of standard. It's you find this in some textbooks, but I don't think this is widely appreciated. This is not usually highlighted in lectures or introductions to differential geometry. Namely, is the remarkable fact that if you consider the construction that takes smooth manifolds, so for a moment x and y are just ordinary smooth manifolds, in particular Rn's and Rm's. If you consider smooth manifolds, and assign to them their smooth functions with a pointwise algebra structure, with their algebra structure by pointwise addition and pointwise product, in R, regarded as a plain real and just a plain algebra over the real numbers, the algebra of smooth functions on Y here, the algebra of smooth functions on X. Then, of course, this construction is functorial, contravariantly functorial, in that we have a pair of these smooth manifolds, then a smooth map between them, a smooth function, can be used to pull back smooth functions from Y to R. So these are functions to R and from X to R. So we can send a morphism here, which is a smooth map, to the algebra homomorphism, which is the pullback operation of coordinate functions, or functions on Y to functions on X. And it turns out that this assignment is actually fully faithful, which can be surprising. This is sometimes known as Milner's exercise. Doesn't even have a real name. This is fully faithful. The fully faithful congruent functor from smooth manifolds into the opposite category of commutative algebras of the real numbers. This being fully faithful means, right, as you know, it means that you have a faithful image of everything you do kind of in the category of smooth manifolds inside here. But of course, this category is much larger. There are many algebras, of course, which are not the algebra of smooth functions on a given smooth manifold, many of them. So that means that, in a way, we've embedded ordinary smooth manifolds into a vastly richer category, inside of which we now have room to generalize our basic test spaces, because these were essentially smooth manifolds, or the Rn's. Another way of saying this is this says that this is familiar actually from algebraic geometry, of course, where the same thing is the case for affine schemes. They're kind of defined this way, right? But what this means is that differential geometry, which is very unlike algebraic geometry in general, is actually kind of closer to it than the definitions may have suggested, in that these smooth manifolds do behave like affine schemes of sorts, in this sense that they also are faithfully characterized by the algebras of functions. And we can use this to generalize our test spaces. So we're going to now define or consider a slightly larger category. We used to be speaking about this very simple category of Cartesian spaces, and we want to enlarge it a bit. And I'm calling it thickened Cartesian spaces. You should think of thickened in the sense of infinitesimally thickened. We want to add some halo around our smooth manifolds, which is just a little bit larger, consisting of kind of infinitesimal directions it may have. So the intuition on the left here, it's again a kind of bootstrap process. We have an intuition on the left, and we kind of make it a reality by defining it to behave as it should. So we want to be speaking about objects in this category which are meant to behave like at the beginning. At the beginning, this is again a bootstrap definition. We do not yet have this product, but it will become true in a moment. So they are supposed to behave like Cartesian products of an Rn, say a plane, times an infinitesimal direction of them, or infinitesimal directions of dimension m here. Something that looks like a Cartesian space, but being just, say, the order k infinitesimal neighborhood of zero, of the origin of that space. Well, what do we mean by this? Well, we can just say, well, under this embedding here, we can actually characterize the functional algebras on these things. If this boldface D here is meant to be of infinitesimal extension and of dimension m, sorry, then it should be the case, and this was what I mentioned at the very beginning, is how physicists think about infinitesimals. Then I want to be thinking about its functional algebra as just being kind of the smooth functions modulo, where every k plus first power of the coordinates I take to be zero, modeling the fact that I think of these functions as being defined in such a small neighborhood of zero, of smaller than modulus 1, that taking some power of these coordinate functions makes them so small that they actually literally vanish. The mathematical way of saying this is we just take the polynomial ring and these m coordinates on m, which I'm calling epsilon already, to the usual symbol for something very small. So think of these as being the small little coordinates along this infinitesimal disk. And just by decree, I say smooth functions on this thing here are defined to be the quotients of this polynomial ring by the ideal, in which the algebra ideal in which every k plus first power of the generators is actually taken to be zero. And you see, my wish now becomes reality again by I can just declare these, since it's a faithful embedding, I define the objects on the left to be the algebras on the right that are of this form. So I just say those commutative algebras, which look like smooth function rings, or smooth rings, ordinary rings of smooth functions on Rn, tensored with such rings of dual numbers, as it's sometimes called, with such quotient polynomial rings. I want to understand these as being the coordinate functions on these infinitesimally thin spaces. And there's an evident, even very trivial way of putting a Grothendieck topology, pre-topology on this. And so we're entitled to the sheaf topos, now no longer on just Cartesian spaces, but on these infinitesimally thickened Cartesian spaces. And we're going to call this maybe that's not the best name. It's hard to find a good name because the terminology is so messed up, but here I'm calling it the category of formal smooth sets, where formal is in the sense of formal power series. It means formally thickened. You should really think of this as being infinitesimally thickened smooth sets, or rather sets that may have a smooth structure, which may have infinitesimal directions. And again, you see we have a very large category, the sheaf topos of generalized spaces, which are defined by the fact that they can be probed this way. And this is, of course, many of you, or some of you, I don't know, may have seen this. This is, of course, the traditional context of what is called synthetic differential geometry. This is what's known as a well-adapted, this is essentially the book topos, a well-adapted model for differential geometry. And in that context, many constructions in differential geometry find, that's where the name comes from, find a very intuitive formulation where infinitesimals sort of actually, not just sort of, they now actually exist. Right? The Yoneda image, or for instance, the first order infinitesimal one disk is the famous infinitesimal interval or something, which now exists in the topos, which is such that it forms the internal Hom, the mapping space, into any smooth set or into smooth manifold. It gives you the smooth space of smooth ways of putting an infinitesimal curve into X, which is just a tangent, turns out to be just a tangent bundle of X. So a whole lot of interesting constructions can be done in such synthetic contexts. But for our purpose here, let me skip over a huge topic and just highlight that once we're at this point, it's actually easy to get to an actual meaning, which again you will have trouble seeing made proper sense of in essentially all the existing literature on mathematical physics of what a classical fermion actually is. Like, as I said before, fermion fields all around us. You consist of fermion fields entirely, almost everything we see and touch. And yet the mathematical foundations of that have actually, if you open any textbook, are quite, or have been quite shaky. But we can very easily make sense of this now by just going one step further, focus on this equation here, or this displayed, whatever it is, diagram. And, we just make one further step. We had previously considered objects, the test spaces, which were kind of characterized by having functional algebras, which were smooth rings of smooth functions on an ordinary n, tensored with some nilpotent ring, thought of as being a ring of functions on an infinitesimal space. Now, what we can just do is we can just slightly enlarge our ambient category of algebras just slightly more to what's called supercommutative algebras, meaning that we assign every element here a degree, either 0 or 1, either even or odd, and just require that odd elements in these algebras anti-commute with each other. So this is a category of very mildly non-commutative algebras, where the graded algebras, Z-mod 2 graded algebras, where the non-commutativity is very mild. It's just controlled by this degree, just odd elements with themselves produce a sign when you switch them. So this is very easily defined algebraically. Goes by the name of Grassmann algebras, which I'm denoting by the usual symbol of this wedge power here. So this just means you form the algebra on Q generators, which where every generator has an odd Z-mod 2 degree, and they also Q-commute with each other. So that's another real algebra. It's no longer commutative. It's called supercommutative. And by the same bootstrap yoga that we applied now several times before, we can now just define a super Cartesian space, which first is just called superspace, as being something that you're meant to, and you are in just a moment, be able to think of a Cartesian product of an ordinary Cartesian space with a superpoint, something that has no ordinary directions, but has Q infinitesimal directions that moreover are graded. And by that we just mean, and we bootstrap it into existence by just declaring the smooth functions on this would-be thing to just be these algebras, tensor products of ordinary rings of smooth functions, algebras of smooth functions, with these Grassmann algebras. And again, there's an evident Grothendieck topology on this. Sorry. Where are we? And we can form the corresponding sheaf topos. And I guess for the interest of time, I'm not going to go through this, but it turns out that in this sheaf topos, the usual fermionic fields, being odd sections of spinor bundles, now exist and satisfy the expected, or not just the expected, the actually necessary relations to the intercommute, which is actually important for those who've ever seen this. Let me just say one sentence for anybody who's ever seen a physics text. You will see, even in the standard model of particle physics or something, people write down the standard Lagrangian for spinor fields. They always look at this form, there's some spinor fields here and the Dirac operator in between. And what is really amplified is that if you just look at this in traditional, as it's usually presumed, traditionally, this is actually a total derivative. It just means kind of 1/2 the derivative of psi square, but psi square in traditional geometry would just if these were just would just vanish. So sorry, no, I mean it would just be you would just have a total derivative. So the usual Lagrangian for fermions, if you do not make them intercommuting fields, would be trivial because they would be total derivatives. Total derivatives in Lagrangians are discarded; they're kind of quotiented out. So it's actually important. It's necessary to even make sense of even writing down, say, the standard model of particle physics to understand in which sense these psi's that everybody writes down are actually, even though they're not defined on complicated spaces, in which sense they're intercommuting. And it's this Topos theory that makes this work. This is not widely known, but here's some references you can find where people actually understood this and described it. Okay, and maybe then finally, even though of course this is not the end of what I have to say, but just very briefly, let me just highlight that in the same spirit, now we bring in higher morphism, higher category theory, reflecting the other main kind of particle in fundamental physics. Besides fermions, the world consists of bosons. And bosons have these are carriers of forces, as people say, and they have the remarkable property that if you have a field of sorts, not yet specified, say it's a superfield, but the super aspect is not so important now. You can just ignore it. But suppose you have some kind of field which is, you plotted it out over Rn. So you have a family of fields, phi, which are meant to be bosons. Then it turns out, physicists discovered this in the 50s, the last century, the last millennium. So it's an old hat, but it's still a deep point. They discovered that it does not make sense physically to ask whether such a field configuration is necessarily equal or not to any other such field configuration. It just does not make sense. They figured out what you have to ask is whether any two such field configurations are what's called gauge equivalent. If there's a gauge transformation between them, there's just physics lingo, or just as good. I mean, that's physics lingo for what in math is called, an isomorphism between distinct but isomorphic objects. And yeah, so one understands that once one has these gauge transformations, they should compose, and they should compose associatively. They should have inverses. So which has the consequence that if we're discussing gauge fields, just like the electromagnetic field, for instance, something very basic, everything like all the computers we're currently using all the technology we're using to give this talk, all use very crucially, of course, properties of the electromagnetic field, which has this very peculiar property that its field configurations, if you probe its field space, you're not getting sets of plots. You're actually getting groupoids of plots. And in general, of course, if you go further, then you actually get higher groupoids and higher gauge theory, which I'm maybe going to gloss over. And maybe just to, in concluding, just to throw around some terminology, if you've ever been interested in gauge theory, you may have run across some of the most sophisticated tool sets they have in hand in order to deal with this are called, I go by these acronyms, BV, BRC complexes. They are algebraic constructions that try to deal with this fact that you're not dealing with sets of fields anymore, but with these groupoids. But in fact, if you understand what's going on, you realize the usual BV, BRC complexes are really just infinitesimal version of these groupoids. In a way, they're just infinitesimal perturbations of the sets we've started with, where you can just talk about what it means to make a tiny gauge transformation. So you're not able in the standard BRC complex speak about what's called large gauge transformations, which control subtle properties of physical vacuums. But of course, and I'll close with that. Of course, with our Topos theory in hand now, we easily see that what we should be doing to globalize this picture is that we model these higher morphisms by simplices, enlarging our category of probes by the objects in the simplex category, which kind of allows us now to probe a space not just by kind of the smooth structure of a coordinate chart, but also ask, well, given that, what are the morphisms from here to nearby, or not nearby, to far away, but gauge equivalent field configuration? And what are the morphisms of these? And this, of course, leads to the definition of higher toposes, infinity toposes eventually, of no longer smooth sets, but smooth infinity groupoids, which I'm just flashing here. And maybe in really closing, I'll just highlight that once one is in this context, one can now make sense of crucial structures that modern high energy physics is concerned with, where one needs to deal with global gauge field configurations and high gauge field configurations. And maybe end with this little diagram, even though it's becoming a bit sketchy now, and that I'm glossing over so many details. But once we're in this context of the higher topos, of smooth groupoids and higher groupoids, there is now a space, which I always call BG-con, that serves as the classifying space in high generalization of how we had classifying smooth sets of differential forms. This now serves as a classifying space for what's called Young-Mills gauge fields, which in particular have associated with it a differential form, namely the Faraday tensor, which measures the electromagnetic field strength that you can measure in the laboratory. But in addition, it knows about what's called the gauge potential over the so it knows about global properties of the electromagnetic field responsible for Aharonov-Bohm effects, solitons, and other structures. And such a thing, such a moduli space now just exists in this higher context, so that maps into it are these fields. And similarly, there's higher versions of this, which play a key role in string theory. Yeah, and so forth. But I guess at this point, I should stop and maybe see if there's questions or if we should just call it a day.
Anybody? Well, speak up if you all have questions. I have a question, just to make it very concrete. You mentioned the Aharonov-Bohm effect. So this is the effect, if people are not familiar, where you have the magnetic field and you go one way around it and you end up with a different spin configuration on the other side. So does that become, I was thinking of that as like a non-commuting diagram, but could you say specifically what you mean by that effect shows up, if you are able, without, I know we didn't cover the details there, but.
Right. No, that's a very good question. Well, first of all, I just mean that the field configuration that gives rise to the Aharonov-Bohm effect is now part of our field configurations. I mean, maybe this is going one step back to what you envisioned, but let's just recall that pre-1930s, for 80 years, since 1850, when Maxwell theory was fully established, people thought that the electromagnetic field is fully determined by, well, the electric field and the magnetic field, which were thought of as being, three vector valued fields on space-time, which together, in the modern perspective, you unify into a single differential two form on space-time called the Faraday tensor. So it was thought that the configurations of the electromagnetic field are fully determined by a differential two form on space-time. For us, a map from space-time X to boldface omega 2 dram. And the important insight of the 1930s in the wake of quantum mechanics was that, in fact, the electromagnetic field is richer than that. It's not just a two form. It's actually locally defined by a one form that has the property that the Raman differential is that two form locally, equipped with certain what's called transition functions, gluing data. They glue these one forms, which cannot exist globally, glues them together in some sense. And that took physicists, quite a long time to really come to grips with what that really means. And just to highlight here, that this is now very neatly captured by this object BG-con. This is described here. Or where is it? Actually, sorry, it's described maybe on the previous page. Just a moment. Yeah, here. So we can very easily now make sense of the globalization of this otherwise confusing picture of what this gauge potential that gives rise to the Aharonov-Bohm effect really is. And then we say, well, suppose we have a moduli space here, a smooth higher space, a smooth stacked BG-con, which I'm again, sorry, which I'm just going to define by what its local plots are, which is very easy. And then I'll just step back and let our Topos theory do its thing, and it will automatically produce kind of the Aharonov-Bohm configurations from that. So what should be the local plots? Because it's easy to say what's going on contractible charts, which is exactly what our probe spaces are like. So we want to say that BG-con is something that, well, if you probe it on a Cartesian space, Rn, forget the Q for a moment, it's just the superposition. Well, it should be a gauge potential on Rn. By what I just said, that just means it should be a one form, traditionally called a differential one form. In general, with coefficients in some Lie algebra. Anyway, it's a differential one form on Rn, such that the de Rham differential of this is our Faraday tensor. The Faraday tensor is assumed to be, or has to be closed by two of the Maxwell equations. And so locally, by the Poincare lemma, we can always find such a one form, and here we pick one. And the only thing we need to add to this is that we, to deal with this issue that this A1 cannot, on a non-trivial manifold, be defined globally, we need to define what are the suitable gauge transformations of this one-form data. Well, by our general prescription of probes, we think of this, what used to be a set of plots, now it's bold-faced to indicate that it's now a simplicial set, a groupoid of plots. So we want to know what are the morphisms in this would-be set of plots. So what are plotting that further out by delta 2 by 2 simplies. What are first of all morphisms in here? Well, these should be functions, again on Rn, the so-called gauge transformations, which transform 1a, say A0 to A1 by a standard formula. If you've seen this, you know it. If you haven't seen it, don't worry for the moment. There's some way of taking a G-valued function, there's in this group, and transform these one forms into each other. And so that gives us a groupoid. And in defining what its composition law is, we need these probes on delta 2. So the composition of two such gauge transformations is just the evident pointwise product of these group valued functions. So this gives us a higher smooth space now, a smooth stack, a smooth groupoid, right? In the sense that you can probe it with smooth probe spaces and these morphism spaces. And now by the general law of higher Topos theory, it now follows that if now your space is, for instance, and now we come finally to our Aharonov-Bohm example, if your space, you take it to be the space-time that is your laboratory, which has this kind of almost infinitesimally long solenoid you have in your laboratory, which for the purposes of that argument we think of as not being part of space-time because you make it so long and have such a strong magnetic field through it that it kind of disrupts space-time structure in a sense. So then we're dealing now with a space that is of the form, R4, Minkowski space-time, minus the world sheet, if you wish, of this solenoid. And that space, of course, that resulting space is no longer simply connected. So as you now evaluate, if you ask them what are the sets, or actually the groupoids of smooth map from such a space-time, your laboratory, to this classifying space, you will find, Topos theory will tell you that, well, you have this local data on one contractible chart, say the right half of your laboratory, and other such data on the left half, and on the overlap, say sort of in the middle of your laboratory, you need to find gauge transformations to glue this data together. And that is, that extra gluing information in a way is what then gives rise to the Aharonov-Bohm effect. Of course, to really describe this, we would have to talk about now what it means to now have an electron coupled to such a background field, which is another story that brings in these fermions that is discussed before. But the punchline here is that the field configurations that gives rise to these non-trivial topological effects in gauge field theories, they are not only neatly encoded by the higher Topos theory. This is really the core. This is what the higher Topos, in a way, right? If you regard it from this physics perspective, this is really exactly what higher Topos theory is about, these gauge transformations. So, if we're in this revisionistic picture where we regard all of high topos theory is from this physics perspective, then the higher toposes are just exactly there to deal with gauge fields. They have this kind of specific local behavior. Does that roughly answer the question, maybe?
That's great. Yeah. So when you're conjugating through G sub I is when you're actually affecting the phase.
Yeah, absolutely, exactly. Yeah, yeah.
Great.
Right. So in the standard Aharonov-Bohm effect, the actual the field would be trivial. The Faraday tensor would be trivial in a sense. All the information is in the transition functions in subset. Yeah.
Great. Thank you. Are there any other questions that people have? I'll go ahead and end the recording here, and then if anyone wants to ask any stupid questions, you're then free to do so.